The last video considered motion with constant angular velocity, and we wrote down a couple of equations for that, and we'll rewrite them shortly. This section wants to consider constant angular acceleration. The development parallels what was done in Chapter 2 with regular or linear acceleration. So I'm really just going to aim more for the results. That'll make this a pretty nice, quick video, I think. Let's suppose that we have constant angular acceleration. That means that the average acceleration, angular acceleration, no matter how we measure that, that's going to equal the instantaneous acceleration at any time during the experiment while that angular acceleration is constant. And then we can take our definition type equations, substitute in, grind through a little bit of algebra, and we reach the conclusions that the final angular velocity is going to equal the initial angular velocity plus the constant angular acceleration times the elapsed time. And also that the angular displacement equals the initial angular velocity times the elapsed time plus 1/2 times the angular acceleration times the time squared. And lastly, the final angular velocity squared equals the initial angular velocity squared plus 2 times the constant angular acceleration times the angular displacement. And we can compare these equations to our constant linear acceleration equations. I'm going to jot those down very quickly just to see the correspondence. Here we had the Vx final is the Vx initial plus Axt, and the displacement was the initial velocity times the elapsed time plus 1/2 times the constant acceleration times the elapsed time squared, and the final velocity squared was equal to the initial velocity squared plus 2 times the constant acceleration times the linear displacement. So the equations match up very nicely, and to a large extent the game can just be played that way. Anywhere you see a velocity, for instance, in an old equation, well, the new equation, you're going to write the angular velocity. If you see the linear acceleration in an old equation, in the new equation, you'll have the angular acceleration. And I think we're just grateful that time is time. I don't believe anyone has ever come up with a rotational time, although that would surely be very interesting. So now, just to summarize, we had our constant angular velocity equations, and those were the delta theta was equal to the constant angular velocity times the elapsed time, or pretty trivially, the final angular position was equal to the initial angular position plus the constant angular velocity times the elapsed time. And then we also have constant angular acceleration, and in case you are scared that I'm going to truly rewrite the whole thing once again, I'll try instead to grab the equation. Okay, it's going to take a little editing here. Computer doesn't want to cooperate. I'm not real surprised. But I'll grab the equations here and drag them down real quick so that we have our list of constant angular velocity and constant angular acceleration equations. These are ones that will get used repetitively in these assignments. And should also make the comment, since we've already introduced radians, you may think that these equations require radians, but they do not. These are valid for any angular units. So you can use these equations with degrees or with revolutions or with radians. You just want to be consistent. It would be silly to mix all the units or pseudo units together. Once you start with one, stick with it. Unless the problem specifies otherwise, you may have to do something else. Anyway, that was a short section, went a little bit crazy. Glad it's over.